out at us, right? Coming out like this. So what's that backside? This back wall to this is what? X is 0. So x is 0 is the backside. And then this front side is this. This red triangle here, which is that equation. So we need to take that and solve it for x, right? Not z, for x. So if we solve this for x, we get y minus z. All right? So this is going to be y minus z. Did y'all see the difference between those two? And now the triple integral. We're going to go, the outer one will be our constant, 0 to 1. The middle one would be from where to where? 0 to y. And then our inner one will go from 0 to y minus z. That, what are we integrating? xz. And then now this part. d what? dx. dz. dy. Let's have the computer do this for us. That was the previous problem, right? That was the one we did before. That's the same problem, but we were just using a different perspective on it. Now we're going to go 0 to 1, 0 to y. That's the same, isn't it? This is now y minus z. xz, but now this is dx, dz, dy. Same answer. Okay? Questions on that? Tetrahedrons are easy to do this with because with tetrahedrons, it's easy to look at this as being like a top surface and bottom surface, or like a left surface and right surface, like this way. Do y'all know what I'm saying? Or if we do it where we cast the shadow on the xz plane, we can look at it as a surface here and then a surface on that side. Do y'all see there's like 3 different perspectives on this one? It's only because it's a tetrahedron that we can do that. So let's do the second part of this problem, which was for us to cast the shadow on the xz plane instead. So it's the same picture, same exact picture, but now when we cast our shadow is going to be a little bit weird to imagine, but do you all see that if we cast the shadow, this triangle right here gets mapped over to that plane? So how do I draw this? X, we're doing x and then z, right? Like that? So x positive direction is that way and z is positive that way. So it's almost like we're looking at it from this side. Yeah. So we have this point comes over to here, this point comes over to here, this point comes over to here. So we have that triangle like that. So that looks like this over here. 1 here, 1 here. Right, so that is our shadow right here. This piece in here. So I think I can do this pretty easily as like a little type 1. My x's are between what? 0 and 1, and then my what's between what? Your z. My z is between like 0 to this top part. So that top part written as a function of x is z equals 1 minus x, or negative x plus 1, right? It has kind of like what we used to call y-intercept is now a z-intercept. Slope is negative 1. So there's your intercept, there's your slope. So 1 minus x. Okay, now we need our restrictions on the y-coordinate. So we got to go back and look at this. This is a little tricky. What are the restrictions on the y-coordinate? This is a little tricky.
X plus z.
X plus z for here? No. I think you're right.
Yeah.
I think you're right. but everyone needs to see y. What is, you're looking at the restrictions on y, so that's this way, right? Like this? Okay, so this side, the furthest side of this the solid object E is this triangle, right? Anything on that triangle has the same y coordinate. It's a constant. What is it? 1. It's this flat surface right here, right? So that's y is 1. The other side is that red triangle again. So it's this plane solved for y. And when you solve that for y, you get x plus z. Do y'all see how that's not 0 to something this time? It's the plane out to that outer edge. Yeah, I don't know. Visualizing this stuff. 0 to 1, 0 to 1 minus x. I apologize. My dad is in the hospital right now, so that might be my sister sending me an update. So what is the order of integration there going to be? No, it's not. dy, dz, dx. There we go. And just for thoroughness, we'll do it. 0 to 1, 1 minus x here. And then this now is 1, and the lower limit of integration was x plus z. And then we're doing y zx. And we should get 1 over 120. Yep. Okay. So that example is just to illustrate how you can have your solid region and you could be looking at it cast on different planes. In this case, we can do it all 3 ways, get the same answer. Yes?
For the y, how can you set it up like first, like for x plus z, greater than or equal to y?
Okay. I'm going to try my best to do this. It's hard because it's 3-dimensional. Okay, so let's do it this way. Let's start here. Let's pick a value between 0 and 1 for x, okay? So let's just say I pick there, right? Let's say I pick that. So now I'm there. Now, based on that x value, I want you to pick a z value that's between 0 and 1 over x. So that would be, you now pick a value anywhere between here and here, right? So let's pick something. Let's just say right there. You see that point? That point right there would correspond to x being somewhere like here, and then the z is somewhere here, right? Okay, now, right now, do you agree that that point lives on the xz plane? To live in this solid, you would have to be between what 2 things? That's what we're trying to do. So I can't be here, right? I need to move myself out into this solid. So to be somewhere in that solid, see, it's so hard to show you, but let's say if I start moving that point in, let's say that's where it punches through that plane. Do you see it? And if I come through, let's say that's where it punches through this wall. Do you see the 2 places? So I've got this little line segment. My y value can be anywhere between where it punches through that wall and comes through this wall. So what is this wall? Well, that's part of this, right? Which is that. So if I solve that for y, I get this, right? And then when I come out the backside, what's the equation of this plane? Well, that's just a constant, isn't it? It's like a vertical plane that just cuts through, and the y value here is 1 no matter where you are. So that's why this is 1. Does that help clarify it? Everyone see that? Okay. All right. Yeah. Let's try this one. I'm giving you a moment to read that while I erase. While you think about that, I'm just going to check real quick. I just want to make sure my sister didn't send me something. So I heard this go off a few times. Nope, this is all. Silence it. Okay, have some time to kind of get an idea of what's being asked here. Triple integral over the solid E. We're integrating the function just z with respect to volume, where E is the solid bounded by the cylinder, y squared plus z squared equals 9, and the planes x equals 0, y equals 3x, and z equals 0, all in the first octant. So when you see y squared plus z squared equals 9, that's a cylinder, right, with a radius of what? 3. And which way does it open? Like, which way does it go? It goes down the x-axis because x is not in the equation. So we have something like that. I'm going to start trying to draw this. It's going to suck, but you know, I know I have like a cylinder that goes like this. Okay? I know, it's impressive. And then I have x equals 0, which is what? The YZ plane, right? So that means I'm basically cutting off the back side of this. So let me do that. All right. Do y'all see that? It's like the back edge of this. Okay. Oh yeah, and it goes, z equals 0 is what? The ground, the floor. Man, this drawing is not good. Okay, so here, this is really not a good drawing. There, that's a little better, I think. It's not perfect, but... So you see how the floor comes through and kind of cuts it? We take the cylinder, we cut the bottom, cut the back, and then I'm in the first octant, right? This is important because that gives me like this, right? And I don't need this anymore. And I have one more thing. Y equals 3x. So what would that look like just like this? Just slope of 3, it would be like this. That's what it would look like. So on the ground over here, man, I'm gonna have trouble with this one. It's like that, right? That's that line over there drawn. And can y'all see what that would look like if I cut that? Look. It's like a little piece of bundt cake. Yes? You got to get up or I'm going to ask you to leave. I'm sorry. Go walk around. Go outside. Okay, so here, 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 here. I don't know. There you go. That's the piece, right? I don't know. How do you get, I mean, this is what's going to be, I guess, part of the challenge for you is getting an idea of what this object looks like, right? Do you feel like you could get to that? No? No? Should we run through any of it? I mean, we can run through it again. This is the back wall, right? That's the back wall right here. Z equals 0 is the ground. And first octant should, I mean, that should pretty much make it be like we're in this room, right? Like here, here in the ground, like we're in the first octant. And then we got this cylinder that's coming through here, right? This way down the x-axis, has a radius of 3. So here's my cylinder coming down like this, right? And then I've got this line cutting through. And you have to remember, this is a plane. It's like a knife that's going to cut through like this. So this is x, this is y, slope is 3. I'm like this. I'm slicing through that cylinder that's coming down with that slice. And that's where that cut comes through, like this. Now, I stopped it here. See how I stopped this? It actually continues forever, right? So that's why we're talking about that and not this just from here to here or something. Practice, right? Homework is where you'll get, I guess, better at it. All right. What now? You got to find boundaries. So you got to start asking yourself, where do you want to cast your shadow? And let's start with the one that is kind of the one we would like to have, which is we start with the light up on top and cast the shadow down. So if we were to shine a light down on this from this object down, the shadow on the ground is that triangle, isn't it? Yeah. So let's take a look at that. That triangle on the ground is in the XY plane. And this is where you have to kind of figure this out. What is that triangle doing? It's this line, right? That's y equals 3x. But then it comes over like this. And where is that at? That's 3. So how do we know that's 3? Because the radius of this right here is 3 because that's the radius of the cylinder coming around. Right? So we know that that's 3. And then if we know that that's 3, then we know what this is. This is 1. Because 1 plugged into here would give you 3. So here's our shadow on the ground, this thing. And I can look at that as like a type 1 region, right? My x's are between two constants. My y's are between two functions of x. So let's start putting the limits on our variables here. X is between what? 0 and 1. And then y is between our two functions of x. Be careful here. 3x to 3. Okay, so our y's, you pick an x between 0 and 1. Now your y has to be between this line and here, so between 3x and 3. And then that would put us, right, that would put us somewhere in here, wouldn't it? Now our z's have to be between, we have to be inside that little bundt cake. So 0, which would be the bottom, z equals 0. And then the top would be where I punch out right here would be that cylinder. So we need to take the cylinder equation and solve it for z, which is going to give us a square root, isn't it? Yeah. And square root means plus or minus, but because we're talking about the top part of the cylinder, we're going to take the positive.
Would you then divide by 2 since it's only the first one?
No, because all that equation up there is giving us is the boundary on our z.
Okay.
It's just that our z has to be between 0 and that curved piece, right? That curved piece, doesn't matter that we're looking at this half. Okay? So what is it? Root 9 minus y squared. There we go. And we're integrating z. So we can set this triple integral up. So we set this triple integral up. We have 0 to 1, 3x to 3, and then root 9 minus y squared to, oh, no, I got that backwards. Sorry. 0 to root 9 minus y squared, and we're integrating z with respect to z, then y, then x. Let's do this one. Let's see if we can crank this one out. Okay, integral 0 to 1, integral 3x to 3. The inner integral, when I take the antiderivative of z with respect to z, I get half z squared. I'm integrating that from z equals 0 to z equals, oh, that's really nice, square root of 9 minus y squared. Isn't that nice? And then dy dx. Okay, when I plug this in, it gets squared. I'm very happy to see that. I still have to hit it with a half, but at least the square root will go away. And then when I plug in 0, it's nothing. So this will be integral 0 to 1, integral 3x to 3, 1/2, and then 9 minus, well, let's just do it this way. 9 halves. You want to do 9 halves? Let's do this. How about 1/2 out of the whole integral? It's a constant, right? Constants come out of integrals. So why don't we do that and then just 9 minus y squared with respect to y then z, or then x, sorry. So now the next integral. Half integral 0 to 1. Okay, when I do the next integral, what's the antiderivative of this with respect to y? 9y minus 1/3 y cubed, and we're evaluating this from y equals 3x to y equals 3, and then we'll integrate with respect to x. This is the first non-trivial one we've had, like where one of them doesn't go, like both of these are there, right? None of them go away. Okay, so let's replace y. Give myself enough room there. First, if we replace y with 3, what do we get? So we get 27 minus 27 over 3, which is 9. So 27 minus 9? 18. So this is 18. Now we go here to here, 27x. 27x cubed over 3. So minus...
18x.
Wouldn't it be 27x cubed over 3, so then it'd be 9x cubed?
Yes. Yes. 9x cubed. Right? So that goes in here, we get cubed, so it's 27x cubed, but then divide by 3, so 9x cubed. And then dx. Right?
Yeah.
Now, let's get rid of the parentheses. I'm going to do that right now by cheating. I'm just going to get rid of this, get rid of that. That's fine. Pass that minus through and pass the minus through. So plus here, and that becomes minus there. That all right? Just saving myself some time. And now I just need to integrate that with respect to x. So 1/2 antiderivative of that with respect to x is 18x minus 27x squared over 2, which I'm going to write that way. And then plus 9/4 x to the 4th. And we're going to take that and evaluate that from x equals 0 to 1. I don't really need to write x equals 0 to 1, but I've done it this whole time. So this is actually going to be nice because when I plug in 0, everything goes away. I plug in 1, this will be my answer. So 1/2, plug in 1. 18 minus 27 halves plus 9/4. Right? And let's have the computer do this for us. It was 0 to 1. You'll have to remind me. 3x to 3. Now I remember. Okay, 3x to 3. 0 to square root of 9 minus y squared. And we're doing, what are we integrating? Just z. That's nice. And we wind up doing dz, dy, dx. 27/8. Is that what we got? Let's see. This is half of 18 is 9 minus 27/4 plus 9/8. So if we multiply 8 here, we get 72/8 minus, multiply 2 on top and bottom there. 54/8 plus 9/8. Again, this is arithmetic. 18, 8, 9, 18, 9. Something ain't right. Hold on. No, that's right. All right. What's this? These two together. 18? Yeah, that's 18/8 plus 9/8. That's 27/8. Okay. All right. So we got the answer, right? So it makes us feel good. Questions? Y'all doing all right? Triple integrals? Let's see what's next. Triple integrals. Okay, this part right here is just me telling you what I already told you, that you can have the shadow cast on, the XY plane, the YZ plane, or the XZ plane, so there's all these different possibilities. I'm really not going to go into any detail, and the problems that you're going to deal with on any exams are always going to be cast onto the XY plane, just for simplicity. Now you may remember this. Oh, you better remember this. This right here gives you the what? The double integral over d of 1 dA is what? Area of d. And I use that to prove to you that the area of a circle is pi r squared, right? We have a new one now. The triple integral over E of 1 dV is the volume of E. All right? So with our last 15 minutes, I'd like for us to prove the volume formula of a sphere. Okay, so if you look in your formula sheets, or if you have this memorized, if somebody gives you a sphere of radius capital R, what is the volume of a sphere according to your formula sheet? 4/3 pi capital R cubed, right? That's our formula. Okay, let's derive that formula. Let's see where it comes from. All right, so the way we're going to do this is as follows. We're going to use this. Okay, we're going to use this. What I'd like to do is I'd like to find the volume of this, right? So I think the best approach here would be to look at just the first octant of this solid, because I think we can handle the first octant. What is the first octant of this solid? If we imagine the x, y, z axes coming through like that, do you all see the first octant being, well, let me see. What's the radius again? Capital R. So this is R here. My sphere would hit here, and it would hit here, right? And then it would hit up here at R, right? And it would, where it cuts through the YZ plane would be there, and then through the XZ plane would be here, and then through the XY plane would be here. Do you all see that? You sure? It's like 1/8. It's 1/8 of the sphere, or the ball, isn't it? All right, let's try and get our heads around this thing. Let's call this E, all right? Let's just call this thing E. And just remember, this is 1/8 of the answer. So I have to multiply by 8 at the end. Let's try casting a shadow onto the ground. If we cast a shadow onto the ground, we get that, don't we? That thing down there. Let's look at that in two-dimensional space. Here's X, here's Y, here's capital R, here's capital R, and it looks like that, right? That's supposed to be like a perfect half circle, but it doesn't look like it, sorry. Okay, let's try and visualize this as being type 1, like that. Do we have X between two constants? 0 to R, right? Do we have Y between two functions of X? Yes, what are they? 0 and?
X squared, Y squared, plus Y squared.
Yeah, so we have to remember that this circle here has the equation x squared plus y squared equals capital R squared, because it is just a circle of radius r, right? So if we solve that for y, we'd take a square root, but we would take only the positive case. We get we get square root of capital R squared minus X squared, wouldn't we? And then what's our Z between? So now you've picked an X, right, between 0 and R. You've picked a Y, which isn't here. So we've kind of gone out here and gone here. Our Z has to be between where and where? Somewhere in here, and we got to punch through this thing. So between 0 and 0 and what?
R minus R squared minus Y squared.
Yeah, we have to remember the equation of the sphere. So what was the equation of the sphere? X squared plus Y squared plus Z squared equals capital R squared. And we solve that for Z, which would be square root of capital R squared minus X squared minus Y squared. Okay, are we all on board?
Yep.
I do not like the look of this triple integral. I mean, the fact is we're going to be triple integral over E of 1 dV. So I'm not really intimidated by this. But I'm really kind of worried about the antiderivative, and once I start like getting these things involved, it seems like it might be tedious and difficult. Right? Yeah? So we're going to do something. This is kind of going to lead us into the next section. Look at this region on the ground. We said it was type 1, didn't we? But what is an even better way to look at that region? Polar. What if we looked at this as a polar region instead? What would this be in polar? So what would change? Instead of using x and y, we would use what? Theta and r, right? Little r. Theta and r. Let's see what would change here. If we change this over, so I'm going to polar right now. If I go to polar, what's my theta between with this shadow region on the ground? 0 to pi over 2. And what's my little r between? That's my little radius I can go back and forth between. 0 and 0 and big R, right? I'm going to be anywhere between here and here. My radius is going to go anywhere between 0 and capital R. Right? Agreed? Now, you may be sitting there going, well, how does that help? Well, come back and now look at Z. Z has to be between here and here, right? But what is this right here for us now? That's just going to be minus little r squared, because when you go from Cartesian to polar, we have this thing x squared plus y squared is r squared. So this now becomes root capital R squared minus little r squared. Do y'all see that? And that will help us quite a bit. So let's try and set up our triple integral. I've switched from Cartesian to polar with x and y. Okay, here we go. What comes first? 0 to pi over 2, right? That'll be our d theta. So d theta is going to be on the way outside. Okay, what's next? 0 to capital R. That'll be my dr. That'll be the next one, right? Then what to what? 0 to square root of capital R squared minus little r squared, right? And then I'm integrating 1, right? R, thank you. I have to have R in there. Why? Because I went to polar, right? Now, what's still here, though? D, Z, and we are integrating with respect to Z. Even though Z appears nowhere, we are integrating with respect to Z. All right, how are we doing? 9 minutes? We can do this. All right, first one. 0 pi over 2, 0 capital R. Okay, antiderivative of R with respect to Z. RZ, and we're evaluating this from Z equals 0 to Z equals square root of capital R squared minus little r squared, right? Once we're done with that, we will do dr and then d theta. All right, so this will be nice when we plug this in. When we plug this in for Z, we'll just have little r times that thing, right? And when we plug Z in, 0 goes away. So all we're left with here is little r times the square root of capital R squared minus little r squared dr d theta. You all with me? Okay, on the side here real quick. If I asked you to integrate r square root of capital R squared minus little r squared dr, how would you do that? U sub, just basic U sub. If I let u be equal to capital R squared minus little r squared, then the big R is a constant, right? So when you take derivative of this, you get 0. Take derivative of that, you get negative 2r dr. You have r dr. Right? So we're going to let that be u. This is our derivative, but we're off by a constant. So I have to scale this thing by negative 1/2. So 1/2, negative 1/2 du equals r dr. So when I redo that, rewrite the integral, I have a negative 1/2 that comes out. R dr becomes du. And the root here becomes root u, right? that. So what is the antiderivative of u to the 1/2? Antiderivative. 2/3. So minus 1/2 times 2/3 u to the 3/2. And the 2's cancel. And you just get, yeah, negative 1/3. This is u, right? So u to the, yeah, so let me just plug this back in now. I'm ready to do the next part. So doing the integral from 0 to pi over 2. And then I just am now doing this integral, right? I'm doing this piece right here. I found the antiderivative of this. The antiderivative of this is negative 1/3 u, which is r squared minus little r squared to the 3/2. Right, that's my antiderivative. And I'm evaluating this where? Where what's what? Where what? What? Yeah, 0 and r, but what's 0 and what's r? Little r is equal to 0 and little r is equal to capital R. So because I was integrating with respect to r, these are my restrictions on r, little r. So what happens, this is just mind-blowing now, integral from 0 to pi over 2, what happens when you plug capital R in for little r? 0, right? That goes away. So you get 0. Then you take away from that what? So plug 0 in for little r, and you get negative 1/3 capital R squared to the 3/2. So negative 1 capital R squared raised to the 3/2. Yeah. And then d theta, right? Okay, what does that turn out to in the middle there? Just r cubed? 1/3 r cubed, right? So when you raise these powers, you multiply them. So that's just going to give you r cubed, but you'll have, did I say negative? I meant to say 1/3. So here's where we are. We have 1/3, right? R cubed, but I'm going to bring the 1/3 out. We have r cubed, and we're now integrating that with respect to theta. What's the antiderivative of r cubed with respect to theta? R cubed theta. So this is 1/3 r cubed theta, and we're going to evaluate that from theta equals 0 to theta equals pi over 2. What happens when we plug in pi over 2 for theta? We get pi, right? So we're plugging this in here. We get pi over 2 times 1/3, so that's pi over 6 r cubed, right? And then when we plug in 0 for theta, we get 0. So this is it. That's the volume. That was 1/8 of it, though. So when we multiply this times 8, 4/3, right? 4/3 pi r cubed. Check. It works. Pretty cool, huh? Pretty cool. So next class, what we will start is 12.6, which is what's called triple integrals in cylindrical coordinates. Now don't let that freak you out. We just did a problem in cylindrical coordinates. All cylindrical coordinates is doing polar. You're converting to polar, but because it's a triple integral, we call it cylindrical coordinates instead of polar. But I'll get more into that later. But yeah, so we'll spend next class doing triple integrals, converting to polar cylindrical coordinates. And then after that, we get a brand new, 12.7 is a brand new coordinate system that we haven't dealt with, and that's called spherical coordinates. All right, have a great day. Remember, your take home is due next Monday, right? Okay. Pretty sure you can do the whole thing now, right? It was supposed to be through 12.5, yeah, so you should